So the next 2 weeks we'll be using that titration method that you used last week to measure the water hardness in different water samples that you're going to collect. We're going to be using, instead of an acid-base reaction and acid and base to determine the end point or the equivalence point of the reaction, we'll be using an EDTA titration, which is, instead of an acid-base reaction, it's a complexometric reaction. So if we look at EDTA, here's the molecule. EDTA stands for ethylene diamine tetraacetic acid. So EDTA, it is a tetraprotic acid, meaning it has 4 acidic hydrogen atoms or 4 acidic protons that can be removed when you put it into solution. So these 4 hydrogen atoms can be removed from this molecule. To ionize it, we need to be at very high pH, pH greater than 10, to make sure that EDTA is fully ionized. But when we do ionize EDTA, now it has a -4 charge, and it actually has 6 binding sites for a metal ion. So metal ions typically have a +1, +2, +3, sometimes +4 charge. And the 6 binding sites come from the 4 ionized hydrogens being removed, as well as these 2 lone pairs of electrons on nitrogen, which will be attracted to the positive charge on the metal ion. So when it is fully ionized, one EDTA molecule will complex with a metal ion and be very stable in solution. It will happen stoichiometrically, meaning that for every 1 metal ion, you have 1 EDTA molecule, and it will hold on to that metal ion very tightly. EDTA is what we call then a complexing agent. It creates a metal EDTA complex, which I'll show you in just a second. But that Y4 abbreviation is what we use for the fully ionized EDTA. So instead of writing out the whole molecular formula, often you'll see this written as Y4-, which means all 4 acidic protons have been removed. Then the HY3- means that only 3 of those acidic protons have been removed, or H2Y2-, etc. And what we have here is the fraction of molecules in the different ionization states as a function of pH. So if we think about being at pH 7, maybe we have a neutral water and we put EDTA in neutral water. You can see that most of my EDTA, about 80% of my EDTA, is in the HY3- form. So I've not completely ionized that EDTA. If we use the deionized water that's in lab, the pH of that water is actually around 5, and so that is worse. We actually have much less of usable EDTA, that H2Y2-, that's actually not going to bind with metal ions very tightly at all. So we need to be at very high pH in order for this reaction to occur. So we're going to pH adjust our solutions to a pH of 10, maybe a little higher than 10, so that we have a lot of HY3- as well as some fully ionized portion here. We're not quite at 50-50. It's more like 60-30, 60-40, 70-30. But that will get us pretty far, so that our binding between the metal ions in solution and the EDTA molecules will be stoichiometric, right? So it'll go to completion, and we can do quantitative measurements with that. What this reaction looks like, okay, we have some free EDTA here in that Y4- form. When we react that with a metal ion, maybe it's a +1, maybe it's a +2, those 6 binding sites that we pointed out earlier will actually be highly attracted to that metal positive charge, and the EDTA molecule will sort of contort itself around the metal ion to capture it. So here we have the metal EDTA complex. And this is called a complexometric reaction. So we create a complex as the product of this reaction. When we do a complexometric titration, it's the same as the acid-base titration that we talked about last week. Titration is a method of quantitative analysis. Okay, again, we're looking for solid numbers whereby a solution of known concentration or the titrant is slowly added to a second solution, which is the analyte. We're going to go until the reaction stoichiometry is complete without excess. Now, in this case, the titrant is the EDTA solution, the Y4- solution, and the analyte is calcium in the water samples that you're looking at. At the equivalence point of the titration, the exact amount of EDTA needed to react with all the calcium has been added. And our indicator, right, we're going to measure the end point, not the equivalence point, using an indicator. Then we use the stoichiometry and do some unit conversions in order to determine, based on how much EDTA was used, how much calcium is present. Now, the indicator for a complexometric reaction is of itself a complexing agent. Okay, so just like in an acid-base reaction, the indicator was an acid, right, that changed color depending on whether it was ionized or unionized. In this case, your indicator is a complexing agent that has a different color depending on whether it is bound to the metal ion or if it is free in solution. And so before we add any of our titrant, before we add any EDTA, the metal ion, some of the metal ion in solution is actually bound in a complex with an indicator molecule. That binding is not so tight that EDTA will actually displace that, and the indicator will be free in solution when the EDTA displaces the indicator molecule. And so in that case, the indicator will actually change color because it's changed its shape in solution. So I have an animation for what this looks like. You can see here that we have a bunch of calcium atoms and ions in solution, and some of them are bound with indicator. So you typically don't add so much indicator so that all of the calcium is bound with indicator, only a little bit. Okay, so that as you start to add EDTA into solution, that EDTA will complex with the free calcium ions, and the solution will still look red until you've complexed all of the free calcium ions, and then the EDTA will start to displace the calcium ions that are complexed with indicator. Once the indicator has been kicked off of the calcium ion, then it changes its color from red to blue. So we started with a red solution. As I start to kick off red indicator molecules, they turn blue. And now you can imagine if we have a mixture of red and blue, we have a purple looking solution. And then when I have just complexed all of my calcium ions with EDTA and kicked off all of my indicator, I no longer have purple and I now have a blue solution. So the complexometric indicators that we would be using would be something like areochrome black tea or calmagite. So there's these two indicators, those are the molecules. And this is what they look like in solution. When it's complexed, when the indicator is complex with calcium and you haven't added any EDTA yet, it looks like a pink red wine color. When you get close to the equivalence point or close to the end point, it turns purple. So half of your indicator is still complexed with calcium ions and the other half of the indicator is now free in solution. And once you have removed all of the indicator from all of the calcium ions, then all of your indicator is blue. So we're looking for a pink color that turns to a blue color, and this is a fine, fine distinction. But if you have a blue endpoint next to the solution that you're trying to titrate right now, it's easier to see the difference between purple and blue. So when we do this titration, again, we have the titrant in the burette. In this case is going to be the EDTA or the Y4- solution. The analyte is going to be a water sample that you're going to place in the Erlenmeyer flask, and then you're going to add that indicator into the water sample. aside from doing the titrations themselves, we still need to standardize the EDTA solution, like we did standardize the sodium hydroxide last week. In this case, we're going to use calcium chloride. So we're going to use a calcium chloride solution of known concentration. You're going to weigh out that calcium chloride and dissolve it, and then use your EDTA solution to titrate that. You're going to calibrate the titration method with deionized water blank also. Basically, this is adding only water, deionized water, into the base of your analyte, into your flask. So there's no analyte, there is only deionized water, and you run this titration the same way you would run any titration, except now it's going to happen much more quickly. And maybe a few drops, maybe a milliliter, but this blank titration allows us to correct for any contribution from the deionized water that we might put into that system. Then we subtract the volume dispensed in the blank titration from all the trials. So conceptually, this is very similar to what you did with the spectrophotometer. In the colorimeter, when you did dyes in drinks, right? You calibrated the colorimeter with blank water, just deionized water, to say, I know nothing is here. There should be 0 concentration. And so I could subtract that absorbance measurement from all of my other measurements, which is what the colorimeter did. Okay. The calculations for this titration are exactly the same as the calculations that you did for the acid-base titration then. We use the concentration of EDTA and the volume of EDTA dispensed to determine the number of moles of EDTA dispensed. Then you use the moles of EDTA and the reaction stoichiometry, which is 1-to-1 in any EDTA titration, to determine the moles of calcium in solution. We then use the moles of calcium in solution and the volume of that water sample, right, to determine the concentration of calcium in solution. We are going to have to convert this concentration into the appropriate units in order to compare it to our literature values, or what we found in our research. But in general, the strategy for solving this titration problem is exactly the same that you used to solve the problem in the acid-base titrations.